All right, we are on schedule to get started with today's live stream in just a minute. Welcome to everybody who is already watching. This is our weekly live stream for computational research methods. We are wrapping up our last couple of sessions of content where students will be able to finish their last assignment and last project. We are in, if you want to follow along in the textbook, we are in Computational Physics by Mark Newman. I'm going to be flipping through section 9.3, Initial Value Problems. That starts on page 418. We are going to continue with our look at how we solve partial differential equations computationally using difference equations. Before we get into the physics, though, I do want to confirm that Jacksonville University is concluding its spring semester online. The mandate for online instruction has been extended to, I believe, June 20th. So we will be finishing the spring semester online. We will not be meeting back together in person to conclude this class. Again, as I said before, I assume that your number one priority right now is your health and safety, and so the deadline for the last assignment and last project is understood to be flexible. So students, please let me know if there is anything you need, anything I can help you with as we finish up this semester. Also, if you are registered for summer classes, that also means that the summer semester will begin online. It may, if that date gets extended, it may be concluding online as well. I don't know yet. If you are taking a summer class, now is a good time to find out from your instructors what they expect of you, what kind of technology you need, what kind of software you need. Do you need a webcam? Do you need access to, Zoom, whatever? Now is a good time to find that out. They may not have an answer yet, but now is a good time to ask, just to kind of get ahead of that train, so to speak. All right, I think that's all the business we need to talk about. So let's recap a little bit about how we handle partial differential equations. So this is the picture we looked at last time, where you've got a two-dimensional grid. This works in any number of dimensions that you want to work in, 3 dimensions, 4 dimensions, 12 dimensions, whatever. We're going to work in 2 for simplicity. So we've got an x-axis and a y-axis. And last time we were interested in the electric potential phi, that's colloquially called the voltage. We were interested in this phi at any given point inside this square, right? So phi is a function of both x and y. And in order to study this thing, we have to study a partial differential equation. Last week we looked at Poisson's equation, which involves a second derivative of phi with respect to x and a second derivative of phi with respect to y, which means the stuff we learned about ordinary differential equations, we can't really apply that here because ordinary differential equations assumes you have one independent variable. Here we have 2 independent variables, x and y. And so really, to solve a partial differential equation problem computationally, you have to convert it to what's called a difference equation. It's basically like going backwards from derivatives back to slopes. Right? So you remember in Calc 1, you had this wonderful day where you finally stopped talking about slopes and started talking about derivatives. Well, computers can't actually handle derivatives, so we have to go backwards. We have to go backwards from derivatives to slopes. And the way we do this, we have to adopt a little bit of notation that the computer can understand. So we take our x coordinates, and we're going to splice that up into a grid, which we're going to label with the integer I. So you could think of, we're replacing x, the continuous variable, right? X can be any number along here, but x sub I is a set of discrete values that we have along the axis here. So they're each separated by a distance, h or a or dx or whatever you want to call it. It doesn't really matter what you call it. Our textbook is going to be calling it a, so I've got it set up as an a in the code just to match. And then for y, we do the exact same thing. We divide it up into discrete points. but I need these two variables to maintain their independence, right? X needs to be able to change apart from Y. Y needs to be able to change apart from X. I need to be able to go and hop to any point in the square that I want. And the way we do that in the computer is give Y a separate index J. So you have to practice your handwriting a little bit to make sure your I's curve to the right and your J's curve to the left to make sure that those are different. You can really use any integer label you want. Other common choices are K, L, M, and N. You especially want to avoid I if you're using a complex equation, which we are not in this case, but like if you work with a Schrodinger equation, you don't want to label it I because then you get it confused with square root -1. So anyway, once you make that little substitution, once you change these continuous variables into a set of discrete variables, then you just have to follow the rest of the recipe. So for example, your dependent variable phi, your function, transforms into a thing with two indices because phi is a function of x and y. There's a different value of phi at each point inside the square. And so phi gets two indices. You can kind of think of it as like the difference between a vector and a matrix, right? So this is like a vector. It's a one index thing because it's got one set of values you move along. This thing is like a matrix. It's got two indices because it's got two directions you can move along the x and along the y. And so once you have that set up, then setting up the derivatives is just a matter of adjusting the i's and the j's. So for example, when I want to take a derivative with respect to x, what I'm looking at is moving along the horizontal direction. So I'm looking at changes in I while I keep j constant, right? That's what a partial derivative means, is that you are changing one variable while keeping the other variable constant. Well, in this notation, that just means you're changing I, you're looking at I to the right and I to the left while keeping j consistent. I could be wrong about this, but I don't think you ever need to have a thing where I and j are changing at the same time. I could be wrong about that. It's been a while since I had to work with a problem where we had to do that. So I don't remember having to do that. So what you're doing is you're looking at a point to the right and a point to the left. So what it means is you're taking one hop this way and another hop this way. And so that means you've got a change in x of 2 times h, right? Because you're looking at one space to the right and one space to the left. When you want to take a first derivative with respect to y, you just change j instead. So you have a j plus 1 and a j minus 1 instead of an I plus 1 and an I minus 1. The only other tricky part is when you have a second derivative, which is most often the case in physics. We like our second derivatives. The universe seems to like second derivatives. What you have to do is a little more nuanced. You have to go a point to the right and a point to the left, and then you have to look at the point in the middle, because what you're doing is you're looking at how much the rate of change is changing, and so you have to apply this thing twice. And so you end up with phi I plus 1, phi I minus 1, minus 2 phi I, and you keep j fixed at each one of those. And because this is a second derivative, the measure in the bottom is squared, so our step size gets squared. So you have an h squared in the bottom. And then again, same thing with y. If you want to take a second derivative with respect to y, you just change the j's and leave the i's fixed. And so that's pretty much how that works. Last week, we took a look at how this works out in Poisson's equation, because we have two second derivatives here. We got one with respect to x, one with respect to y. And so we apply the prescription once for the x derivative, once for the y derivative. And what you end up with is an equation that you can solve for phi. Because if I could figure out what phi is at a particular point, then I've got the phi everywhere. And so what I have to do is I have to look at the point to the right, the point to the left, the point below, the point above, and then I've got my rho ij, my charge density function here. But the most important piece is this piece right here, where you're looking at every point around it. Really what you're looking at is the average, right? Because you add up 4 things here and divide by 4. That's an average. So really phi is based on the average of all the values around it. And so before we move on to talking about how this works out in terms of initial conditions, I do want to ask whether there are any outstanding questions about what we've looked at so far. I forgot to do this earlier, excuse me. Let me get you the link to this thing. I think I just have to copy this, copy and paste. There we go. So before we move on, I just want to check whether there are any questions outstanding from last week. You can let me know in the chat. You can let me know over email. Either way. Okay, while I wait for questions to come in, let me get my next board set up here. Let's see. There we go. All right, I haven't seen any questions come in yet, but please keep those coming in. There is a little bit of a lag between what I say and what you hear, so feel free to post any questions you want in the chat. Okay, what we want to look at today is how we have to treat the problem a little bit differently when we have a time derivative, right? So Poisson's equation back over here, it's just a function of x and y. It's not a function of time. So we're assuming a static case for phi, where it's only a function of x and y. There is no time dependence. But when I have something like, say, for example, the heat equation, like this is an example of a heat equation, what I have on one side of the equation is a derivative with respect to x and a derivative with respect to time. And at first you say, okay, I'll just do the same thing I did before, right? I already saw how to do this part, and so I can just replace my d phi dt the same way I did before, right? So I have to make phi into an I and a j, and we'll let x be labeled by I, and time be labeled by j. And so what you're thinking about instead of a two-dimensional grid is you're thinking about maybe a rod or something that goes along the x direction, and you've got that split up into pieces here. So this is going to be, you know, x0, x1, x2, x3, etc., etc. And then you're also thinking of this as time equal to 0. So you're thinking of this entire line as being t0. And then we want to move that forward to time 1, right? And so the way to think about it, I'm not drawing my grid space in the same way. That's okay. The way you might intuitively think about it would be, okay, I'm just going to move forward in time 1. So I'm going to have a snapshot of the rod at time t0. I'm going to have a snapshot of the rod at time t1, a snapshot of the rod at time t2, a snapshot of the rod at time t3, etc., etc. And so you might think, okay, great, I'm just going to apply the same prescription I had before. So I'll have a phi I j plus 1. I'm going to move forward one step in time, minus phi I j minus 1, a step backward in time. And I'll divide by 2 times dt, just like we did before, right? This is exactly what we did before. I'm just calling the step dt since I've got a time step instead of a spatial step. And this would work. Let me pause for 1 second. The cat wants out of the room. Go, go, go. Go on. Go on. Come on, there's food outside. There you go. Okay. Okay. Sorry about that. And you might think, okay, great, that's fine. I'm going to just use the same prescription. But there is a problem, because whenever you wanted to get t0, that means you would have to go backwards in time by 1, right? So I would have to go to time minus 1, and I don't really know what a time -1 is, right? It also means if I wanted to get t1, I'd have to go backwards in time 1 to t0. Okay, that's not a problem. But I would also have to go forward in time 1 to t to t2. I don't really have a way of doing that, right? Because I haven't figured out what t2 is yet, right? We can get around that in the spatial direction, because I have these endpoints over here, right? So I can keep propagating forward what I don't know to the endpoints, which we kept fixed. But for time, yeah, the universe doesn't work that way, right? So what we have to do, we have to make a little bit of a change to this. So what we're going to do instead is we're going to take only one step in time, right? So instead of going to a time before and a time after, we're going to keep the current time over here. And so in other words, we're only going to take a step of dt instead of a time of t. And that's going to avoid us having to worry about this whole time -1 business, right? So we're going to put a no sign over that. That's not allowed. Right? And so with this structure set up, I can solve for phi I j plus 1 and solve this whole equation for that and end up just incrementing this forward. And so basically what we're having to do is treat the time derivative a little bit differently than our spatial derivative. And that is okay. We are allowed to do that, right? This is all an approximation anyway. This is an equally good approximation compared to what we used for the x. We're just basing our approximation based on the information that we have. Okay. So let me show you what this looks like in practice. I'm going to open the file here for our project number 3. I've emailed this to you. Let me post this link in the chat just so that you've got access to it. If you don't already have Jupyter Notebook open, I would recommend going ahead and opening that. Let me get shareable link. Project file for Jupyter Notebook. So if you don't have Jupyter Notebook open already, go ahead and do that so we can look at this file together. This is based on a sample code in your textbook, Newman's Computational Physics. It's based off of the sample code on page 421. Basically, this is using this method we just used. So this is called the FTCS method, forward time centered space. That's a fancy way of saying what we just went over, that our time derivative is moving forward, right? We're going from the current time to the next time. But our spatial derivative is what the textbook is calling centered. So in other words, we're going to the right and to the left. We're treating that with a nice symmetry there. And so what we're going to study is the heat equation. The way the heat equation works is that you have you've got the temperature in a rod. So we're looking at a rod over here. We're going to go from 0 to L on the rod. And just like we showed before, we're going to divide this rod up into pieces. Each of these pieces is going to be a distance A apart. So that's going to be our grid spacing here. It's going to be A. That's going to be our step size in X. And what we're interested in is the temperature at each point in the rod. So in other words, I'm interested in the temperature at point 0, the temperature at point 1, the temperature at point 2, etc., all the way up to the temperature at the last point. Actually, I guess that should be point N, just so I'm consistent there. Erase. There we go. Temperature Tn. There we go. And so what the heat equation assumes is that a given point here, let's say T1 here, is going to change based on the concavity nearby, right? So for example, if T1 is at a minimum, is at a local minimum, and it has a positive concavity, right? A minimum has a positive concavity, then that means that its derivative with respect to time is going to be positive. That means its temperature is going to increase, right? That makes sense. It's next door. Think of this in terms of atoms. Here's an atom at a lower temperature. Here are two atoms at a higher temperature. These things are going to interact, and this atom is going to end up coming up to a higher temperature because it's near higher temperature atoms. Let's suppose we have a point over here near the other end of the rod that's at a maximum. So it's kind of hogging all of the thermal energy over here. Well, that means it's at a minimum, which means its second derivative is negative, which means its time derivative is going to be negative. That means it's going to be decreasing, right? It's going to be giving thermal energy to the neighboring atoms. And it's a pretty simple model. It's nice because it gives us a second derivative over here and a first derivative over here. The only other piece is this D here. This is the thermal diffusivity of the rod. It's basically how quickly does that interaction take place, right? So if you have a low thermal diffusivity, the atoms tend to hold on to their thermal energy a lot longer. If you got a high thermal diffusivity, they tend to share their thermal energy a lot. So you can think of it as the level of social distancing that the atoms are practicing. So to get started, we need to set a set of boundary conditions and an initial value for the temperature at each point in the rod. The code is going to give us a graph of temperature versus x for selected values of time, right? So this temperature is going to be a function of both x and time, and I just found a typo in this. So if you have this open, you can change that dt squared to a dx squared. My bad. I will get an updated version of this loaded. Let me put that in my to-do list. Upload corrected project 3. There we go. A type of mistake you only find on video. Oh well. So let me show you what the end result looks like. This is what the end result looks like. We got the temperature versus x. So you can think of this length here as literally being the points along the rod. This is what the temperature looks like in the rod at each moment in time. So we've got a snapshot at 0.01 just after we started. We've got a high temperature on the left, a low temperature on the right. And you can see we haven't had a whole lot of thermal energy diffuse yet, right? Because we've got a peak over here and a midpoint over here, and everything else is just kind of average. A little bit later, we start to see things level out in the yellow curve. And then in the green curve, things really start to level out. Eventually, what we're approaching is a final state at 10 seconds, where we've got a fixed point up here and a fixed point down here, and everything else just kind of falls linearly in between the two. Right? Now, if this thing is a line, if this purple one is a line, that means its concavity is 0, which means temperature dt is 0, which means we've reached a steady state, which is great. So I want to walk you through how we get this information. So I want to walk you through how we create these separate plots at these particular points in time, and how we time evolve the temperature function here. Because what you're looking at is the same function t, but it's been time evolved as we move forward in time. So let's take a look at how things work. First, we import our usual libraries. You might need to import some extra stuff here to complete the project. Excuse me. Here we've got our length of the rod. We're going to do this in units of meters. So this thing is, I guess that's 1 centimeter? I think it's steel in meters. Yep. Okay. Yeah. So that's, oh, excuse me. Yeah, that's the thickness of the steel. Oh, right. Because he's thinking of this as like as a slab. Okay, that's fine. Here we've got the thermal diffusivity. That's just the value chosen for steel, I'm guessing. I'm going to splice this up into 100 points. You know by now that if we increase the number of slices, we're getting more accurate results, but you saw those graphs. It's pretty smooth. Here's our step size. You shouldn't need to change this. Just change it by changing 100. And then here's our step size in t. So our textbook calls this h for some reason. I would prefer dx and dt, but we're going to stick with what the textbook has. Yes. Good. Okay. And then this value epsilon, you're going to see why this is important in a second. This is just a fraction of h. So think of this as a tolerance value for t. That's going to be important in a minute. Here's where we get to our boundary conditions. This is the stuff you might change to explore this problem. We've got the low temperature at the right end. We've got the high temperature at the left end, and the middle temperature. This is what your guess is for the beginning. It doesn't really matter what number you put in the middle. It's the boundary conditions that really matter, but this is the temperature in the middle. Actually, excuse me, this isn't a guess anymore. This is actual time evolution. Yes, this part does matter. I misspoke. Excuse me. Yeah. So that, it needs to be, actually it doesn't even have to be a value in between those two. We could change that around. All right, we'll play around with those numbers later. Next comes the interesting part. This is the new technique that's being used in this code that we have not used before. This is where you select a set of time values where we're going to create the snapshots of the temperature graph. These are the values that your textbook used. You are going to add to these for the project. I'll show you what that means in a minute. But basically, this is a list, and you're saying these are the temperatures that these are the times that I want graphs at. So you see you got a 0.01, 0.1, 0.4, 1, and 10. Down here you got a 0.1, 0.01, 0.1, 0.4, 1, and 10. So whatever values you put in that list are going to end up on the graph. We'll see why in a second. And then this part just tells the computer where to stop. It's saying, I want you to end the simulation just after the maximum value. So go one step past the maximum value, just to make sure we capture that maximum value. So epsilon is your fudge factor for the time values. Excuse me. So here we're going to create the arrays for the temperature values. We're going to start with just an empty array, just so we've got something to work with. Here we're setting the boundary conditions. We got our high value and our low value. High value is at the left, low value is at the right. The left end is at T0. The right end is at Tn, right? Because we have this thing divided up into a grid. We're going from I equals 0 to I equals n. Then here we're setting the middle value. So this is a fancy way of saying set all the values from 1 to n at t mid. So this is a nice little shorthand instead of having to do a loop over all those values. This colon here just means go from 1 to n. And I'm guessing that is not inclusive of the endpoint. That's usually the way Python works because we just set tn up here. So it's going 1 to up to, but not including n. And then here we're creating T prime. So this is basically the next temperature value. So kind of like what we did with the relaxation method, we're starting with our initial array. We have to move to the next one. So we're going to temporarily hold that in TP here. And then here we're also setting TP's boundary conditions. Right, so this is literally just setting up the arrays. Once you change values up here, you shouldn't need to change anything down here. This is all just going based on the information you provided above. All right, here's where we get to the physics part. This is where we are moving forward in time. This is the chunk that's going to show up in the equation, right? So when we go to solve this equation over here, when we go to solve this equation for phi ij plus 1, right, we're looking for the next value. So phi here is the temperature, so just mentally replace these phi's with t's. When we solve this, we're going to end up with, I didn't put a d in for the diffusivity, I'll add that now. There we go. You're going to end up with multiplying by your diffusivity here. You're going to be dividing by your distance step size here and your time step size here. So that's what all of this hd over a squared is. It's just your distance step size squared, your time step size, and your diffusivity value, right? That's just taking care of all the numbers that come along for the ride when you solve it for the next one. And this is what you get when you solve it, right? Because when I come over here, if I wanted to solve this thing for this, first I would be multiplying by dt. So that's where that combination comes from. And then I would be adding this to the other side over here. And that's exactly what you have over here. You have the previous time, or excuse me, the current time value. So the next time value is the current time value plus c times, and here is your, this is your second derivative, right? You have t, you have temperature at the right, you have temperature at the left, and then you have temperature at the current point. So this is just the second derivative. Now this is doing things a little bit differently than we did last time, because this is using this colon value to do math on the entire list at once, right? So last time, what we had to do was loop over I and j, and we were updating each point individually, right? So you had phi prime equal to phi with all this stuff. This is doing that same math. This line here is doing that exact same math. It's just doing the loop for you. It's this neat little shorthand that Python has. When you're working with an array, you can do math on the entire array at once. So what it's doing is it's doing the loop for you, and it's a little bit cleaner. It's a little bit easier to write. You're not having to stare at a loop within a loop. So that just makes it a little bit easier. If you don't like this, if you would like to go back to this version, you are welcome to do that. And I wish you the best of luck. But you don't actually have to change this line. So, you might as well just copy and paste it. Here's another neat little shorthand I learned recently. You can swap two variables by having t, tp equal to tp, t. So this is literally swapping the places of t and t primed. And then here we got to increment t, so we're going to update t. So this is the part that's taking care of all of the physics. And this will get you at each point in the loop your next temperature value. So this is the only line with any physics in it. Everything else is just getting the method, the code set up. Next, we come down to making the plots. So when we go to make the plots, what we're looking for is, am I at the point in time where I'm supposed to be making a plot? Because if I'm not at one of those selected times, right, if I'm at anywhere in between these values, if I'm at 0.2 or 0.3, for example, I didn't ask for a graph, so I don't want the computer making a graph. So what we're doing is we're saying for each time in the list, that'll be what TL stands for to keep it different from T. For each time in the list, we're going to ask if T minus TL is less than epsilon, right? You can't ever ask Python whether two things are equal, right? You can ask if integers are equal. You can ask if strings are equal, but you can't ever ask if two floating point variables are equal, because there's always going to be that difference, right, between, right, because you're always going to end up asking it, is 6.00001 equal to 6? And it's going to return false. It's going to return a big old false. Even though you and I, as humans, would say, yeah, it's true. They're basically the same. You should count that as true. Python is going to count them as false because of the stinking 1 out here, because it's always going to have that little bit of error. So by doing this, what we're asking is, we're kind of cheating and asking Python, is 6.00001 approximately equal to 6? And it'll say true for that. Right? Because what I have to do is I have to tell it what my tolerance factor is. That's what epsilon is my tolerance factor. And so what I'm doing here is saying, is T and TL close enough to be equal, right? Because it's not like, right, we're asking them if they are within 1,000th of the step size, right? Remember, each of these time values in TList is separated by H. We're asking if T and TList are within 1,000th of H together. That's only going to trigger once. There's no way that can trigger more than once based on the way we have this list set up. And so what it does, it says, if that's true, if we're at one of the magic selected values, create a plot of the temperature, and I've given it a label, time equals the listed time value, just so we can tell which way this thing is evolving. And so that's where this comes from. That's where this graph comes from. If I wanted to add more to these, like let's say I wanted to see what happens between the green and the red, right? Things are starting to get linear between green and red. I know that I want more data points between 0.4 and 1.0. So all I have to do is come up to the list and add a few points. I'll just add, let's say, a 0.6 and a 0.8. And that's going to get me 2 more. Let's click run. That's going to get me 2 more plots in the graph. See, I've got more data in there now. I go from 0.4 to 0.6 to 0.8. I've got more traces on the screen here because I was able to add those. Let's suppose I want to see what happens between 1 and 10. I can add more data. I can add more time values here. I can add, let's say, a 3, a 6, and a 9. And it's not even going to take me any longer to run the code because I'm just running graphing commands. It's not like I'm telling it to go farther up in time. And here I'm kind of filling in the picture here. Now, obviously, if I put in too many of these, I'm visually not going to be able to tell what's going on because they're going to be too dense together. But this is just to give you an idea of what's happening kind of in the snapshot there. Okay, so that's an overview of how the code for Project 3 works. I want to take a minute to ask if there are any questions on what we've looked at so far, and then we'll spend our last few minutes taking a look at what you're going to be asked to do in Project 3. So let's pause for a minute and let me know in the chat or over email if you've got any questions. You know, while we are waiting for questions to come in, let me save this and upload this update so that it's got the right variables in there. Manage versions. There we go. It's a neat feature on Google Drive where you can click on manage versions for a file, and then you can upload new version. Obviously, if you're doing something with Google Docs or Google Slides, something like that, it automatically save. But if you're uploading a new version from your computer, this is a way to keep that link the same and not have to send out a new link to everybody you're working with. What am I looking for? I'm looking for PHYS 251RI, Project 3. There we go. Awesome. Okay, that has been updated for you. I should probably send that out in an email as well. All right, I haven't seen any questions come in, so let's take our last few minutes to look over what you'll be asked to do in Project 3. So what I'm going to ask you to do is, in the space below, copy and paste the code from above. So I would like, I realized, if I have you edit this, then the graph goes away and you don't have that benchmark for what you're looking for. So what I ask you to do is take all this, copy it, and paste it into here. And what I want you to do is, inside the while loop, I want you to have the temperature at the leftmost end change according to a sine function, right? So the way this works right now is that the endpoints are fixed, right? This endpoint is fixed at 50. This endpoint is fixed at 0. I'm assuming that's 0 Celsius, not 0 Kelvin. But let's imagine we put a heat source on the left-hand side that was varying the temperature up and down, right? Well, I'm allowed to do that, right? I don't have to keep that fixed, because really what's happening here is you're only modifying from 1 to n-1. You're not actually modifying the endpoints. And so you could change T0 in here. So what I'm asking you to do is, inside the loop, is to add in a T0 equals this function that we have down here, right? So you can take this here. You'll need to import NumPy's sine function and NumPy's pi value. That's not a problem. You've learned how to do that now. And so I want you to put in this varying function here. I want you to put in the sine function in here. All you have to do is come in and put in T0 equals this. So you're updating the majority of the rod through the difference equation, but you're updating T0 based on this fixed function here. And I want you to select some time values for snapshots to show how this changes the behavior of the temperature in the rod, right? So you'll have your kind of benchmark here of what the rod looks like with fixed endpoints. And then I want you to have this T0 changing. And then you can kind of, examine the graphs. You can kind of compare the two. And I want you in this space here, in this markdown cell, to discuss your results. So what looks different? What looks the same? It's a nice, easy visual comparison. That should be pretty straightforward. Once you get sine and pi imported, so like from NumPy, you can just import sine and pi, right? Once you get those imported, you can get this function into here to say t of 0 equals this function of time. Run the code, select some t values. The ones that provided might be enough, or there might be some more that you want to add in to look at. And I'm just asking you to describe what difference that makes. That's it. Should be pretty straightforward, unless you run into some technical issues, which I encourage you to email me about or ask me about in office hours. Should take maybe half an hour, something like that. And that'll give you an idea of how to work with these difference equations with time. And that's it. That's the last two things you're asked to do in the course, is this Project 3 with the heat equation and this final assignment with Poisson's equation. So with that is everything I have on my notes. Next week, what we'll do is we'll continue with the live stream, but I'll just take that time for questions from folks. I'm happy to repeat anything that we've been over or re-explain it or go into a little more detail. I will have office hours in about an hour and 20 minutes over on Google Hangouts. I'll send you a link to that. I'll also have office hours Monday at noon. Feel free to have your Jupyter Notebook files open, share your screen, show me what you've got so far. Would love to see what you've got and see what feedback we can go over together. So with that, I'm ready to call the formal time to a close, and we can take some questions over chat or over email. All right, I haven't seen any questions come in, so I will hang out for another couple minutes. Otherwise, I thank you all for your time. I wish you the best for the rest of the semester. As always, please let me know if there's anything I can help y'all with. I hope you have a great weekend. Bye-bye.